Hello, everyone. In this section, we are covering comparing two population means, or mu, where sigma is known and our samples are independent. Let's go ahead and get started with some definitions, starting with, well, I use the word independent there. What does that mean when we're discussing these with respect to samples? So two samples are independent if the data from the first sample are not connected to the data from the second sample. Two samples are dependent if they are systematically connected or paired. Okay, so here note that we are looking at independent samples, so these are not going to be connected to one another. Now, our formula that we will make use of here is going to look similar to the ones that we've been making use of. And let's just take a look at what are the conditions we need in order to make use of this formula. So when both population standard deviations are known, the samples taken are independent, simple random samples, and either both sample sizes are at least 30 or both population distributions are approximately normal. Hey, that's our central limit theorem again. The margin of error of a confidence interval for the difference between two population means is given by, our error is z sub alpha over 2 root sigma 1 squared over n1 plus sigma 2 squared over n2. Note that for our previous ones, that was going to be z sub alpha over 2 times sigma over root n. This here, note, it's very similar, only instead of just sigma over root n, we have the sum of these two together. So note that it's the same basic idea as sigma over root n, but it is the sum of these sigma squared over n. For each of our samples. Okay, and same basic idea for our conditions. Okay, so let's just see how we can find some of these, and then we'll go ahead and calculate them. All right, so let's take a look at this example here. Consider the following statistics computed from two independent samples chosen at random and their corresponding population standard deviations. Assume that an 85% level of confidence is desired to estimate the true difference between the population means. Calculate the point estimate and calculate the margin of error. So here, our point estimate, well, very similar to what we did before. Our point estimate is just going to be where we take our sample idea and use that in place of our population. So instead of the difference between the means mu1 minus mu2, we're going to use x1 bar minus x2 bar here. That's going to be 7.01 minus 6.93. This is going to give us 0.08. This is our point estimate. B wants us to calculate our margin of error. So this one is just going to be our E equals Z sub alpha over 2. Now, looking at my table, Z sub alpha over 2 for 85% is 1.44 for this 0.85 times square root sigma 1 squared. Sigma 1 is 2.1, so 2.1 squared over n1, which is 48. Plus sigma 2 squared, 1.8 squared over, this is 30. By the way, note samples greater than 30, so we don't need to worry about our conditions. We're going to take 1.44 times the square root of 2.1 squared over 8 plus 1.8 squared over 30. And we get approximately 0.644. Okay. Now, a thing I should mention here as a reminder, when we are looking at an intermediate calculation, we'll want to keep as many of these digits as possible. So here, I'm just going to round it to 0.644. But if, for example, we were using this as our standard error when we're trying to find our confidence interval, then we would write as many of these digits as possible. Okay. Well, when we are looking at our margin of error here, as a reminder, it's just going to be the same basic idea of what we've been doing before. The lower bound of my confidence interval is going to be this here. And my upper bound is, of course, going to be the same thing, only plus my error. Okay. And there we go. So this is going to be our confidence interval. So let's go ahead and take a look at an example here. A researcher is looking at the study habits of college students. A random sample of 42 freshmen reported a mean study time of 15.0 hours per week. A random sample of 39 seniors reported a mean study time of 23 hours per week. Construct a 95% confidence interval to measure the true difference between the amounts of time taken per week that freshmen and seniors spent studying. Assume the study times for freshmen have a population standard deviation of 4.7, while the study times for seniors have a population standard deviation of 5.2. So for this one, I'm just going to start by writing everything down and noting what is what. Okay, so here my N1 is 42. My X1 bar, 15.0. And then my sigma 1 is 4.7. My N2, which is my second sample, is 39. My N2, or rather my X1 bar is going to be, or X2 bar rather, is going to be 23. Then my sigma 2 is 5.2. Okay. So all I've done is just properly labeled them. And then I'm going to note what is my alpha here and what is my confidence. And my confidence is 0.95, which means my alpha is 1 minus that, 0.05. So my alpha over 2 is 0.025. So then my z sub alpha over 2 is going to be 1.96. Okay. All right, so now that I've got this stuff, let's go ahead and get started with first, let's just find our point estimate. It's going to be x1 bar minus x2 bar. This is going to be 15.0 minus 23.0. Let me be precise here with my units. And I get negative 8.0. Okay. Now, my error is going to be z sub alpha over 2, 1.96 times square root of 4.7 squared over 42 plus 5.2 squared over 39. Okay. And then plugging it into my calculator, 1.96 square root 4.7 squared divided by 42 plus 5.2 squared over 39. All right, and let me just double check that I've entered everything correctly. Okay, everything looks, double check here. I think everything's fine. Yep, all right, everything looks fine here. So then this is approximately 2.1643. Note, you want to round it to as many as possible. I'm actually not even going to use this number here. This is just for bookkeeping purposes. I'm going to use it directly out of my calculator. So I'm going to note negative 8, and then start with minus for the lower bound. Negative 10 point end here. As a reminder, since we are working with stats rather than data, we are going to be just rounding to the next data point, or we're going to be rounding to the same level of precision as the standard deviation. So this is going to be negative 10.2 and then negative 8 plus this number here, which gives me negative 5.8. Okay. So we can say to a 95% level of confidence that the freshmen are studying on average between negative or 10.2 hours less to 5.8 hours less. Okay. And there we go. Hopefully that makes sense to everybody here. So this is how you go about doing that by hand. Pretty simple, pretty straightforward, same basic thing. Get your stuff, use your C to find your alpha, alpha over 2 to find your C sub alpha over 2, use your point estimate that we've been doing, use your formula for the error, plug that in to find your interval. Okay. Now let's discuss how we can go about making use of our calculators in order to expedite this process. And for this one, we're going to go ahead and make use of this example here. All right. So it says an automotive repair shop advertises that using a fuel additive will decrease the wear and tear on an engine. An independent researcher collected data from 50 randomly selected cars that used the fuel additive and found that the mean cost of engine repairs was $3,250. And he then collected data from 55 randomly selected cars that did not use the fuel additive and found that the mean cost of engine repairs was $3,445. The population standard deviation of engine repair costs that do not use the fuel additive is known to be 812. Assume that the population standard deviation of an engine repair cost for cars that do not use the additive is 748. Construct an 85% confidence interval to estimate the true difference between the mean costs of the engine repairs for cars that use the fuel additive and those that do not. So for this, we're going to be making use of a 2-sample z-int test. So for that, what we're going to do is we're going to go to our stat tests. We're going to look for 2-sample z interval. Okay, 2-sample z interval. And we are going to use stats. All right, so sigma 1, so this is my standard deviation from my first population, which is standard deviation, 812. For my second population, 748, or my second sample rather. No, that's population. All right, anyway, X1 bar is going to be my 3250. Oh, I believe I mixed these up. It was for the fuel additive, and this is fuel additive, yep. So do be sure that when you're reading through these, you are careful which is going where. So this is 748. And actually, this is probably a good idea just to note what my sigma 1 is, my x sub 1 bar is, and my n is for these. So my sigma 1, which is going to be the ones that do use the additive. So for those that use the additive, this was, my sigma was 748. X1 bar was 3250. And my n here was 50. Sigma 2 was 812. X2 bar was my 3445. And my n for that one was, I believe, yep, 55. All right. So now that I've got this organized a bit better, I'm less likely to make that mistake. All right, X2 bar. And X2 bar is 3445. And N2 is 55. Right. Confidence level 0.85. Now we're good to go. So again, everything seems to be correct here. So I find that my confidence interval is negative 414.2 and 24.16. So I can say with an 85% level of confidence that it is going to be between this area here. Can I conclude that it's going to reduce the cost? The answer is no, because note that 0 is included in this interval. And I can't say that, oh, it's more negative here, so that means it's actually going to be less. It doesn't work that way. Remember, this is just saying what is the probability that the true difference of the means in our population is equal or is found in this interval. It's not saying that it is this, it's not saying that it is this. I just know 85% it's in here. So that means it's possible that it actually is costing more. So just something to be aware of when you are looking at these numbers. Anyway, that is all that I wanted to cover for this section. Let me know if you have any questions or want to see any additional examples. Otherwise, I will see you in the next video.